Hey, this is Scott. I'm going to do a second part of this um, matrix algebra, linear algebra in R. Just a few basic concepts. This is part two. I did part one earlier, so you might want to check that one out. And if you hopefully you can see my screen. The things that we're going to talk about today are covering the inverse, orthogonality, eigenvectors, eigenvalues, also called characteristic roots, some spectral decomposition or eigendecomposition, SVD, singular value decomposition, QR, and Cholesky uh, decomposition. All right. So let's just dive into it. This should be fairly brief, and I'd like your comments if this is useful. Because if it's not, I'm going to probably stop here. I have a lot of different interest in things that I can do. So anyway, let's look at the definition of a matrix. Right. So I'm going to define X, this matrix, using the matrix formula. By the way, when I say native, I mean that I'm not having to load any libraries in here. All the R natively comes with all these functions, so you don't have to load any libraries from CRAN or anything. All right, so I'm going to create this very simple matrix, a 3 by 3. So I enter it in, number of rows, and I just enter that, and sure enough, I get what I'm expecting along the diagonal 2, 3, 5. 0 otherwise. So an inverse, and we'll call it x prime, or really the inverse of x, is such that x prime, that's x transpose, is equal to x transpose x, which is equal to the identity matrix, which is a diagonal matrix of ones along the diagonal and 0 otherwise. So in R, we use the solve function. All right, so the inverse of x is solve x. And then if I do that, then this is the result that I get for that inverse. And so if I want to do a check on that to make sure that I got my definition correct, again, this is the way that we multiply two matrices in R. So there we go. Now we have an identity matrix 1, and then also if I do x inverse times x, then I get the same thing. So I've checked my formula off here. So that works. Okay. So now so definition of an orthogonal matrix. Matrix is invertible if it's orthogonal. So let X be a K by K matrix such that X, this should be inverse. X inverse. Anyway, inverse X is equal to T. It's said to be orthogonal. All right. So why do we even care about this? It turns out that a lot of statistical problems are, it's full of examples where we need a tractable inverse, which means that I can, with a closed form solution, calculate it. I don't have to use a numerical or simulation. I can actually just use math like we just did and come up with an inverse. So a lot of problems. In fact, ordinary least squares here, simple linear regression. So if you solve for the coefficients in multiple regression, the vector b is actually equal to the inverse of x transpose x, x transpose y, where where this little sign that I have here is the transpose. We prefer to have an inverse, but if we don't, there are such things called pseudo inverses. So we won't go into that, but it can cause problems if you can't create an inverse and programs will fail sometimes due to that. All right, so eigenvectors. So let A be a k by k matrix and x be a k by 1 non-zero vector. Then an eigenvalue or characteristic root of A is the number lambda, such that A times x is equal to lambda times y. I'm sorry. A times x is equal to lambda times x. So let's just do an example. All right, so I have a very simple matrix here, a 2 by 2. Let's look at that. We see what that looks like down here in the console. And then to calculate the eigenvalue, I just use this function eigen. And actually, that function provides both values and vectors. So this is the values, and then here are the vectors. And I'm going to go ahead and, because I'm going to do spectral decomposition here in a minute, I'm going to need to strip the normalized eigenvectors out of that. So I'm going to create this lambda 1, lambda 2, and just to look at what that looks like. And then the eigenvectors themselves, E1 and E2. So now I have both the two vectors and the associated eigenvalues, and I can look at that. And then the spectral decomposition is this formula, right? So the spectral decomposition is equal to lambda 1 times this matrix plus times E1 plus lambda 2 times matrix times E2. So if I do that, then that comes up with spectral value there. And then I don't think R has a native way to do that, possibly. But anyway, that's the way to do it by hand. Anyway, so singular value decomposition. So this is a factorization of a real or complex matrix. So why do we care? Factor analysis in statistical methods and dimension reduction. Those are two areas where you're going to want to be able to do this. What that means is, let's suppose you have 1,000 columns and you just want to 1,000 columns, 1,000 variables, and that's too many, and you need to reduce that set. Then you can use singular value decomposition or factor analysis to come up with a subset of that provides most of the statistical power within a smaller subset. And then when you do whatever method, machine learning method or statistical method you want to apply, then you don't apply it across the 1,000. You just apply it towards, maybe the top 10 or 20 of the actual variables themselves, because that's where the power of prediction would be. So how do we do that? We use this SVD function, right? And then there's 3 values that are returned. So we get the vector of the singular values sorted in decreasing orders, and you can see that in the console, 17.7 and 4.5. And then also the matrix of the left variable, the original matrix, and then of the corresponding right as well. And then just 2 more quick functions. One is QR decomposition. And so to do that of A, we use that function there. And again, Cholesky factorization for symmetric positive definite square matrix. And so we'll do that. And so, and that helps. And there's some requirements for every one of these, right? The matrices have to be invertible in some circumstances, and et cetera. So there are requirements, but that's used a lot in Monte Carlo simulations, and I did another video on Bayesian Monte Carlo Markov chain and that's used in Bayes a lot, where you're doing numerical solutions. So again, hopefully that was useful. Let me know if and that helps me determine what to add to the channel, whether it's Bayesian inference, math, concepts, etc. Thanks.